was actually a follow-on to the paper I did last year. It was about basic tuning on the server side of things and how to get the most out of the hardware you have. The biggest problem you have in benchmarking and storage today is that you don't actually try to eliminate the bottlenecks on the system, because some of them you can't eliminate and some of them you can work around. We know that from our own research on some of the systems we put into the field that tuning the back end of a system is really key to getting good performance. Now that's not a static setting, it's something that you have to change over time, etc. But it also turns out that as we go forward in newer releases of Lustre, there is a lot of new Lustre releases being brought onto the market now that has features that we didn't have before. Those clients, for different reasons, need to be tuned differently depending on what version we're using. Now, that may be good from a benchmarking point of view. It may not be appropriate to all the applications run, but at least it's a good start to figure out which parameters are really the key. So what we did is we took a look at Lustre, some of the features in here, and we specifically wanted to look at a number of standard features. One of them is the wire checksum that is done over the wire, which is a safety precaution to make sure that we don't have bit flips in flight, etc. Now, most people will tell you that there's a significant performance impact to the system, which is tribal knowledge. Actually, I've never actually seen anybody measure it. So we decided to do that since we had enough time in our systems to do a lot of things. Then we also wanted to look at some of the changes we are now doing in the marketplace on RAID layouts and what we can do to optimize performance in that layer. We looked at the different client versions that we are looking at, that we now have available to us, and the tuning parameters of those clients, or some of them. There are so many different ones and we can't tune it all. And in the end, we added the bonus feature, which is not in the paper, which is looking at different ways of doing I/O, whether it's buffered or direct I/O, and if there is any major difference between them, and if we can tune around that problem. So I wanted to add a lot of different things in here. So I'm not going to do a lot of preamble. I want to get to the results, and then we can have a discussion at the end. First of all, the way we've done storage, specifically Lustre, for a long time is using standard RAID 6. There are some companies using RAID 5, but honestly, I think that's a danger to your data if you don't have at least RAID 6. Now, that's all good and well. The way we used to do it is we had a standard set of 10 drives using standard RAID 6, 8+2, and a hot spare within our enclosures. Our enclosures happen to be high density enclosures, but they're similar to anything else in the marketplace when you have more than 24 drives in enclosures. There are 84 drive enclosures out there, there are now 96 drive enclosures out there as well. So there are different ways of slicing and dicing your data. What we did is we actually took the entire volume we have available, 41 drives, and made it into a single RAID volume. Now, that poses a bit of a problem, especially if you're using RAID devices or disk drives that's larger than 4 terabytes, because that means you break the 128 terabyte limit that you have at the moment. So we've had to do some workarounds, some fixes, which is now part of the open source code going into the community on how to actually extend it to at least 256 and beyond. Now, the reason why we did that, the new distributed parity, is really around not getting different performance, not getting benefits in that area, but having faster rebuilds. So the way we designed this, and this is our implementation. Now, there are other implementations in the world. Not everybody is similar, but the way we do it is we have this volume, and in this case, every one of these lines is a disk drive. We arbitrarily distribute a block and the associated parity all over the disk drive. So it's fully stochastically distributed, or parity declustered as the original terminology is. We actually based our algorithm on the original paper from back in 90 that outlined this, but they couldn't build it back then because they didn't have the CPU power to actually drive it. Now, we can do that today. We still keep it very basic. So we're doing, out of 41 drives, we do 8 disk drives, or 8 data drives, 2 parity drives, and 2 distributed spare drives, stochastically distributed. Now, the spares are the white lines. We actually have them close together in a single stripe. So when you have to do a rebuild, you don't have to scan the disk drive to find that spare drive. It's actually a distributed part of the system. And that means we can rebuild a system much faster than traditional RAID. Now this is still software RAID, still software driven. But we can do this we can actually take a 6 terabyte drive, rebuild that in about 9.5 hours, which is some of the requirements you have on data resiliency out there. And we can do that without having too much impact on performance. Now, any other vendor you talk to, or any other open source code you look at, if you actually use parity clustered RAID, people, the user would tell you compared to traditional MD RAID, it will give you about 5 to 10% performance decrease. Now we decided that that is an acceptable penalty to get better reliability. But as it turns out, this actually works to our advantage in the systems for different reasons I don't have time to go into, but we can always ask questions about that later. So we're using what we call grid RAID, which unfortunately is a marketing term that I didn't agree with, but I didn't have a choice here. I think parity declustered RAID is still a better word for what we're doing. The benchmark setup was really simple because as an engineer in a big company with unlimited resources, engineers don't get much, unfortunately. So we had a single previous generation enclosure with some of the hardware. We had 8 clients that we could run QD only because we didn't have enough FDR, HBAs, LACAs in the system, but it's enough to saturate a solution. We ran it on our compiled version of Lustre, which is Lustre 2.1. It's for all intended purposes the same open source community that you can download from Intel. There's no major difference. The only reason is we take it down, we recompile it, we fix certain things to fit our hardware a little bit better, but it's the same open source code. So there's no secret hidden magic in that. You can do the exact same thing with a stock version. We use standard OFAD, we use Scientific Linux 6.5, and it's very much everything available to anyone. So there's nothing hidden, there's no magic in what we do here. This is just an idea, but you can actually see what the rack looks like, and that will actually be the only product slide I have in there. And the reason why I show this is just to how do we map that to a Lustre file system. Well, you have the main data service, this is 2.1, so that's those 4 rack units up there. You have the OSS pair, which is those 5 rack units at the bottom. That's all the disk drive there is. 84 disk drive in total is doing the entire file system here. And then we have a couple of clients stuck in the middle. Actually, that's 8 clients. There's 2 quads that we're using for our systems. Not even the latest and greatest, but it's enough to saturate the system. So that's our entire system that we had to benchmark. Now, if you compare that to a place like Blue Waters that has 36 of these racks and they're all full, there's a little bit of a difference from a benchmarking point of view, but you take what you can get. So sorry about that. Now, we like IR, or I like IR. There are other choices out there, but the reason I like IR is that it's very true to what you're doing and it uses MPI, which most of the applications we do does as well. You can get the same results with IOZone if you want to. You can even get the same results with Bonnie++ if you really tweak the hell out of the system. But IR seems to be the most accepted benchmark tool out there, so that's what we use. We did not change any specific parameters in there. We kept them stable. If you compare to last year's paper, we model around a lot within these, but this year we kept it stable. The significant thing that we did is we are using, for single thread, very large block sizes. 1 terabyte block sizes or half a terabyte block sizes, because we not only want to go beyond what memory can do, we actually want to push it a dimension beyond that, so we're sure that everything is done doing disk and no caching whatsoever. And we also started using stonewalling. I don't know if everybody knows what stonewalling is, but instead of starting a process, see it ramp up, run, and then it ramps down, which is what a single process would do, we look at sustained throughput. We get it up to the maximum, we measure it for a couple of minutes, running at maximum, and that is the performance you can get out of the system. It will give you slightly higher numbers than a single run would do. However, it will give you a more true throughput of a system under sustained load can do. So that's one of the reasons we're doing that. Now, that's also how you see some of the larger companies in the world delivering compute does a benchmarking. Cray, for instance, only uses stonewalling. And most other companies do that as well, because it gives you a more consistent value of the system. We use a standard stripe count of 1, so we don't actually stripe over multiple units. And we use a standard stripe size of 1. Now we could have used 4 megabyte IOs because we've actually backported them to our 2.1 release. But again, that's a future release in 2.4, and we did not want to change the basic parameters. Now, the first thing we looked at was checksum over the wire, because it's been in Lustres in 1.6. It's being used standardly because it's always turned on. Most people actually do turn it off, but it's turned on. One of the problems that it has today is it uses a fairly old checksumming algorithm called ADLER32. ADLER32 is only software-based, there's no hardware acceleration today, and it really has an impact on CPU utilization. If you see a client running this, it will use about 20% more CPU to do these calculations. I said most people turn them off because they don't want to lose that extra overhead. And that overhead, as I said, is from tribal knowledge set to be about 10 to 15% most of the time. Now if you do an InfiniBand, you have a lesser risk of actually having problems with the over the wire because of the peer-to-peer architecture, but it still is there, and it's becoming an issue in a lot of things. I'll talk a little bit about that. Now, in Lustre 2.4 and beyond, we can actually start using other algorithms like COC32 that can be hardware accelerated on an Intel platform to run at wire speed. And that is one of the things that we will do going forward, is starting using different algorithms. Now that actually turns into something else I won't talk too much about, but there's a project that's been out in the open source for quite some time called T10PI or T10Diff, which is doing checksumming from the, well, in essence from the client all the way down to the disk drive, so that you check parity on both reads and writes using a checksum rather than a parity bit. That's something that we started to implement on our new systems. This one does not run it, by the way, but it's something that uses the same type of coding going forward. And this is something you see on a lot of different systems in the world where we need to be able to clearly show silent data corruption on disk drives. Now that's beyond this research, so I won't mention it further. However, we did map the performance impact of reads and writes using checksumming over different clients. As you can see, if you look at the 189 client, at least on read performance, it has an almost negligible impact. You can't really see. On writes, it goes between 10 to 12% literally, depending on what tuning parameters you can do. So on writes, it does have a noticeable impact. Now you look at some of the other clients, 216, we included the 2.1.6 client, even though everyone knows it's the worst client ever built for Lustre. But we still wanted to include it. And you can see that the impacts on writes are just beyond acceptable. On writes, on reads, on writes a little bit more in parity with everybody else, but honestly, the 2.4.3 and the 2.5.1 seems to be a lot better at doing this. Again, we're still using software Adler here. We did not change to some of the new algorithms. But you can see the impact. And it doesn't really change much with tuning parameters, whether you go from 32 RPCs in flight and upwards, because we still have enough CPU to run it without impacting the throughput. But there is a significant impact, so I do understand why people turn it off. So it has to be a choice. You will risk things to get 10% extra performance, or don't. At least now we have some numbers indicating exactly what that impact is. As you can see, it's higher on writes, obviously, since it has to calculate that. But even the reads decoding it when you read it back has an impact on performance. Now, I did mention the clients here that we ran 189 clients, which is the de facto fastest client in the world currently. The 216 clients, which is a mistake, I would say, because it doesn't really produce anything in any of the tests. As you'll see, it's really the outlier here. The 243 client and the 251 clients. Now, those are the latest clients we can get access to at the time. And we've also used them because those are the production level quality clients that is being delivered by us and by Intel and other companies in the marketplace. What we did look at was some of the parameters specifically, as I said, with or without checksumming, but we also looked at the two biggest parameters we found: max RPCs and flights, i.e. how many write or read request can a single client issue to the system in parallel. Now, default is 8. And then the next one is max 30 megabits, which is how many megabytes of information can you cache locally on the system for reads or for writes. It's more important when you do buffered I/O than direct I/O, but it does have an impact on both. Now, default is 32. We know from historical tests, and we did these last year, that 8 and 32 is by no means good enough for any performance. That was from back in the days when we had single or dual core chips. Now that we have a lot more heavily used chips with more cores, that just doesn't suffice. So we went kind of overboard a little bit. We've been recommending 3228 for quite some time, but we upped it up to about 256 RPCs in flight, and that really saturates the number of credits you have on the InfiniBand. So you normally needs to make sure that the InfiniBand has more than the standard 64 credits available, otherwise you can get into credit locks. And 124 or gigabyte of cached data in both directions. Now, these are the raw data we have on reads and writes, with checksums, without checksums. And if you look at that, you can see that on the 189 clients, the reads and for both checksum and turn off and checksum and turn on is pretty much peaks at the same level. Writes is a little bit lower, but still very much in parity with each other over time. You can see that scales up to the full load, running 96 threads total in the system, or 16 per client. Now the scale of all of these are the same, so you can see the 2.1 is really miserable. That is really bad performance, so we don't want to speak of that. And then you have the 2.4.3 and 2.5.2. Actually, that's supposed to be 2.5.1 client. Yet another typo. And you can see that the impact is a little bit larger on the reads and on the writes. But you also see the total performance here. This is peaks at about 7.5 gigabytes per second in the system, and there's peaks around 7 gigabytes per system for reads. Right, and that's pretty much the same. I mean, these are actually different measurements. They look like the same curve, but they're not. There are some subtle difference in there. But it was amazing to see that under these loads, the 2.4 and 2.5 client being so similar. There's actually about a 40% difference in the I/O code of each client between 2.4 and 2.5, because 2.5 has to support HSM, which 2.4 does not do. So there's a lot of change in that code. Both of them support distributed namespace server, which is another one of these bottlenecks in the system. But you get the picture a little bit. They're not quite at the 189 level, but they're close enough to be acceptable, I would say. Now, then we compared what happens when we run a single thread per client. And you can see 189 peaks around 1150 megabytes per second, and none of the other ones come close to a gigabyte per second on the system. And obviously the 1.6 is not even on the chart, I would say. But interesting enough, tuning has no impact on performance of these clients. We actually even ran it down to the default 832, and it's still at the same levels. So tuning on single client performance has no impact whatsoever. It has access to all that I/O, and it doesn't matter. So that was kind of a revelation. We thought we would have effects of the tuning parameters to a certain degree. Now, we started looking at each client in detail, and then we looked at tuning parameters from 189 for reads and writes. And you can see we kind of changed it logically, and you do see a little bit of effect of these, where the basic standard one that we've been recommending for 189 is 32 RPCs, 128, 30 megabit in the system. Is still the one that actually performs best on that system for both reads and for writes. So that wasn't really a big surprise. I do have a slide on 2.1.6, but it's so bad I won't even spend time on it. Now we went into the 243. Okay? 243, and as you can see, there is a lot more difference between the original settings that was good on 189, which is the 32.128, which is actually the worst here. And as you go up to really high lows, 256 RPCs on flight, you get better results. And you have the same pattern for writes as well. Honestly, if we only ran the original settings that we recommended earlier, we would have really dismal results for these. So tuning the parameter, pushing it much, much harder is really key. And again, the pattern with the 251 is very, very similar. As you said, all of these are data without checksums. We actually turn them on for these tests. Now, we also looked at some of the parameters between buffered. As you say, all of these runs were also done with direct I/O. So we wanted to look at what happens if we actually do the exact same test but with buffered I/O instead. Didn't change anything else, ran the same script, but we used buffered instead of I/O. Now we know that there's a higher CPU utilization on buffered than on direct. There's still a discussion in the field between application owners which is the best. You will find certain manufacturers of equipment always do in direct because it's cleaner, pure, and you don't have the risk of data overrun on the client side. But it also means that you cannot stagger as many commands normally on the disk side as you can. So we compare these, so you can see buffered I/O reads and writes on the hash lines, and the equivalent direct reads and writes on the other lines. So you can see on 189, there is a significant performance decrease when using buffer. So we can't really get away with that. On the 216 clients, again, not as much difference on the high-end side, but it's still way below the other clients. The 243 and the 251s are closer, but you still see that direct I/O is faster on both of these with implementation. Now, anyone remember our paper from last year know that in order to get good performance using similar parameters but using a standard MD RAID system, we actually had to do direct I/O to get the read performance anywhere near acceptable, whereas write performance was better with buffered. Now with this system we don't have to muddle around because the grid RAID component does give us a more even I/O pattern. But it's interesting to see that you can tune these much higher to get this performance, even on the 2.3 and the 251. That's almost in parity with this one. I have no idea why that suddenly dropped down. So if you actually look at these parameters, just to looking at how do you actually optimize the parameters, you also see I used the one that gives the best overall results here. So the 128 on those, and we went to 256 on those, just to get more performance in the system. Otherwise we would have a bigger difference. But I try to get an equal amount of performance out of the system, or the maximum amount of each client, and those are the numbers that actually generate that. Now I showed this slide last year, and it's still just as true, but we wanted to look at just a little bit of parameters. How much does the CPU on the server side, not on the client side, but on the server side, actually matter? And what happens, and what happens if you add a little bit more SAS to the system? So the latest version of our solution, we've actually upgraded the CPU to an Ivy Bridge instead of Sandy Bridge. We upgraded with another 4 SAS lanes going into each disk layer, so we have 12 lanes of SAS instead of 8 lanes of SAS, still 6 gigabit SAS. It's the same disk drives, same enclosures, same everything else. And you can see a single OST is now peaking about 4.5 for direct and just a little bit lower than that on buffer. Now, if you look at those 4 OSTs, that 4 OSSs, that's a slightly larger system than the one we tested otherwise, but we had a little bit more when we did this test. The basic idea here is that suddenly we get 50% more performance with a very minor change to the CPU. Going to a 10-core Ivy Bridge instead of an 8-core Sandy Bridge gives us 50% more performance in the system. But that's the only change there is in there. And that means that we can hit about close to 18 gigabytes per second out of 2 of these, or close to 9. So, you know, small additions to that, changing nothing else, really improves performance. But the important thing, I think, when you look at this is when you have more CPU power, suddenly your buffered IOs and your direct IOs get very close to each other, which is really the takeaway from this slide. So in summary, and you can actually read them for yourself, I don't want to spend too much time on that, but the effects of wires, checksums over the wire is really significant, and it has an impact. Going to hardware accelerated will change that and make it better. I think that's an important change that we need to do, and the community as a general need to learn how to do. The use of a parity clustered RAID configurations really helps as well, because it will allow you to have a better yield of your disk drives, giving more push into the system because you're not sharing the data with more object store clients on the server. You have one object store client per object store server, and that means you can streamline the I/O much, much better. This is even more significant when you go to Lustre 2.5, and I don't have any data I can show you on that yet, but it does have that same effect. Moving to a more modern client is really key, because we want to start using some of the new features, whether that be in HSM, DNE, NRS, all these nice abbreviations I don't have time to explain in detail, but some of the new stuff that goes on, which is something I've been looking for a long time. Specifically HSM is really key to a lot of the enterprise customers we have, but distributed namespace servers is also very, very important. And some of these systems going in over the next future is going to be heavily used in those. And just a word on that, 2.5, I still haven't seen a production system in the world running 2.5 of Lustre yet. There's a lot of tests being done, but to my knowledge, the first launch system that will go in is a system we start building in Hamburg in January. There will be more than 50 petabytes of usable storage space, controlled by a total of 13 namespace servers, one traditional MDS and 12 distributed namespace servers. Honestly, I have no idea how to do that yet, but we'll get through that. Number 2, client tuning parameters. Basic bottom line is you need to push the system much, much harder than you did any other system when you get to these new environments. And I don't care if it's our hardware or somebody else's. I'm betting that if you take the latest NetApp solutions or the latest DDM solutions, you have to do the same to get maximum performance out of the system. You need to push the clients to really utilize the CPU architecture you have on the site. This will change again when we get to Haswell. I don't have access to that yet, but once I do, we will definitely repeat those as well. Then we have the direct and buffered I/O. Now, I'm a fan of direct I/O because that means I'm not relying on anything, any paging, anything going on in the system. It's really much cleaner from an I/O. And if you have problems debugging direct I/O, it's much easier than debugging buffered. But some applications do buffered and cannot be changed to something else. So you need to know how to understand. You need to understand how you can tune that specific component, and it can be done. But again, it's a little trickier than direct. But I will leave that be out of that. So my final conclusions is, and if you haven't figured out, I'm rambling by now, so I will try to get out of this as well. The choice of a client is really key. Now you choose a client not because it's the fastest client. If that is the only thing that matters, stay on 189. You can actually compile a 189 to run at Scientific Linux or Red Hat 6.5 without any problems. It's not rocket science to do that. It's easy to do and it runs really well. It's not made for that one, and it can't utilize all the benefits of that kernel, but it can run it. If you need anything more modern than that, DNE, HSM, imperative recovery, data on size of metadata, etc., you need to go to a 2.x client. It will currently come with a performance impact, but we're working with the community to improve that. And finally, don't rely on traditional tuning parameters because they will not work on newer systems. Figure out what works in your environments. Now, we can come with some recommendations. You can find what we did here as a guideline. It will not work for everyone, and I think that's an important lesson as well. So with that, I think I'm pretty much done.
All right, Torben. be a question?